Primary. Hello students, welcome to our lecture where we will introduce the subject more closely, and as I said in our introductory video that we will discuss the motivation that why we need to understand water resource systems and manage them. So in this lecture I will discuss the aspects of water resources systems, what constitute a water resource systems, some real world examples, and then I will also discuss other application areas where these concepts can generalize with more specificity. And then we will also discuss that how the solutions that we are learning in this course can also generalize to sustainable water resource management practices. So let's get started with the intro to water resource management. And when we talk about water resource systems, let us see that what constitutes a water resource system. Now, whenever we talk about systems, systems could be defined as any structure, device, scheme, or procedure wherever we have some input and some processing is done on that, and I will represent this processing by this Greek single symbol ohm, and we or omega, right? So input processed by some processor here. This could be simple fx, or it could be a complex functions that has multiple components, and all these add up together to give us an output. So this input and output, they are related by certain transformation, and this transformation could be simple or it could be complex. And whenever we try to relate this input and outputs through sequence of events, we call that we are working on a system. And when we talk about water resources systems, water resource systems are complex. Most of the times they are large scale, and they are very important for to the society as well as the ecosystems that surround that particular water resources system. Now, in the hydrology, I understand many of you might not have learned hydrology so far, but there is a concept called as a catchment or watershed, which should not be difficult to understand. So we define catchment as a funnel in which any drop of water that falls into that funnel, it will go towards mouth of that particular funnel, and anything that is going outside this funnel would be part of another watershed. So water would be collected and then routed, and it reaches the mouth of that particular funnel. So we call this catchment, wherever we define this boundary, that anything and everything happening within this catchment, at least in terms of inflows, would stay here, and through rivers, channels, or streams, this water would be taken to the main river. If you talk about river Ganges, we know that river Ganges has so many tributaries and distributaries. So when you try to draw a boundary around Ganga river basin, you would end up visualizing the watershed that is being traced by river Ganges. And at the mouth, wherever river flows at particular point, from there we can always identify what is the extent of catchment for that particular uh, stream point where we are standing. So for example, if we stand at Sundarbans in West Bengal and try to do a backtracking, we will see that most of the North India would be covered by Ganga river basin. Similarly, when you stand at Haridwar or Rishikesh and you do a backtracking, you would be able to see that catchment that is upstream of Haridwar or Rishikesh would fall into the Ganga river watershed. So depending upon where we are standing, the boundaries of watershed would keep on changing. But one thing is for sure, that any precipitation happening within the boundaries of watershed would be directed to mouth of the river wherever we are measuring the stream flow. And when we talk about storing this water, so what typically happens, that these rivers, they come from mountains or from wherever they are originating. It could be lakes if we are talking about rivers in central or south part of India, because we don't have snow fed rivers there. What we do, we want to use the water for our good, because once this water joins the sea or ocean, it would become saline and would be of limited use to no use for us as far as our consumptive use is concerned. So what we typically do is that at points where we can define a watershed large enough, we can always make some reservoirs and try to store the water. And once this water is stored here, it can be diverted to canals or channels. So in Gujarat, we have this Sardar Sarovar Dam, which pulls a lot of water coming from upstream of Sardar Sarovar Dam. And then it is routed through Narmada Canal, which goes all the way to arid and dry areas of Gujarat. So this is one typical example of a water resources management project. And once this water is stored here, it would be used for irrigation. Some water would be also diverted downstreams because there would be cities and industries downstream of the river. And we have to regulate that how much water would be released for canal, how much water would be released for industrial project, and how much water would be released for the irrigation project. Now, one thing is for sure that whenever we are talking about watersheds which are not perennial, what we would have cyclic demands. So, for example, cyclic supplies, I must say that sometimes supply is high, and in other part of the year, the supply level goes down, but we have demand all year around. So, what we want to do, we want to store the water that we are receiving as an excess and use it in the times when we have less supply available in form of or rainfall or other natural sources, and use that storage during the dry part of the year. And specifically in countries like India, where we rely heavily upon monsoons, and in specifically north part of India and western parts of India where we have dry winters, what would happen is that we rely a lot on the storages that we have created during monsoons. And while rainwater harvesting projects may be good at smaller scale, it they may, to meet the large scale demands, specifically in arid and semi-arid areas, we need water resource management projects that can take waters over hundreds of kilometers and help people meet the water demand to survive as well as flourish. And then what happens is that once this water goes downstream, there would be industries located along the coasts. There would be cities and towns located along the banks of the rivers, and they will discharge wastewater into that particular river. And ultimately, towards the end, we have an ocean where this river would terminate. Now, this entire scheme of things, starting all the way from watershed to reservoir, building of dams, using that particular dam for irrigation to generate electricity, and then diverting water downstream for use of cities and industries, constitute the water resource project or a water resource system. You see that we have precipitation as input and stream flows as output. So this is a typical definition of system that we proposed. And also here we have multiple smaller subsystems. For example, watershed can be classified as one smaller constituting subsystem. Dams and its operation would be another subsystem. Canals or channels that are taking off from this reservoir would be another subsystem, and so on. So we are putting large number of subsystems together to form a integrated system that we wish to manage. Also, when we built dams, what we are doing is that we are collecting a lot of water at one specific place, or we are having a stagnated water. And when water is stagnated, some water will go down into groundwater in form of groundwater recharge, and some water would also go as evaporation. And now, if you know that whenever water surface area increases, the rate of evaporation also increases. Also, when large volume of water is in contact with ground, it would be able to recharge or percolate deeply, and hence we have to account for these losses whenever we try to model these systems. And as water resource managers, our aim is to holistically model these components and subcomponents, represent them mathematically, and try to identify what are the objectives. For example, again in the state of Gujarat, our objective would be to take enough water from the canal that it reaches the far lying areas of Kutch and adjoining villages. On the other hand, if you talk about some area which is getting plenty of rains, our objective would be to minimize the flooding that could happen, and hence the objective would not be to store water but to identify enough diversion routes so that whenever heavy precipitation occurs, we should be able to let the dam open and diverge water to the places which really need it. So we would see that different kind of objective functions can be asked or posed to water resources systems, making it challenging and interesting enough. Now, as I was saying, this flood management system. So let us try to look into this example of watershed. So we have a watershed, and then we have some reservoirs, reservoir 1, reservoir 2, reservoir 3, and there is some irrigation land that we have to take care of. Also, there is a town here. Now, what would happen is that whenever there is a heavy precipitation upstream, that water would be channeled through the reservoir or held into reservoir. But once the reservoir reaches its capacity, we have to release some water from here. And there are two other smaller reservoirs marked as B and A. And if these reservoirs also are opened at the same time, there are chances that the town that is located just downstream of these reservoirs may get flooded. And we commonly see that in many towns of India, specifically in Bihar, uh, there are certain rivers that have their dams upstream, maybe in other countries or just at the international borders, and and because of opening or breaking of dams, these flooding scenarios are quite common during seasons of monsoon. Now, if we do not release enough water, there may be an irrigation patch that solely relies on the water that is coming downstream from these reservoirs to meet its irrigation need. And now we have to prevent the flooding as well as manage the irrigation needs, which where we need water. So we always deal with the conflicting objectives, which makes things challenging enough again. So this is one specific example which we will try to model as we go forward into our courses. Also, there we will be dealing with two kind of approaches. One would be optimization and another would be simulation. What we want to do in optimization is that we want to frame this question as a maximize or minimize problem subjected to certain constraints which are often governed by the policy or logistics that we are dealing with. Policy would mean that this water downstream, this river downstream should have at least this much meters of water flowing throughout the year because we want to preserve the ecosystems or forest land that are falling downstream of the reservoir. So that's a policy constraint. Then another would be logistical constraint that yes, we want to maintain 3 meters of water every time in the river, but we do not get any rainfall upstream during monsoons. So there is a logistical constraint. We have a limited supply of a resource. So we would always deal with the constraints and we want to maximize the social good or maximize the profit or minimize the amount of pollution that we would have in terms of concentration in river. So these would become our objectives and constraints. Now nobody can stop us to define the objective of our choice, and nobody can stop us to define the constraints that are realistic. So if resources are limited, that has to be constrained. And optimization hence has a lot of freedom that how we choose or design our constraints, as it really depends on relies on the experience that we have dealing with the system. On the other hand, simulation deals with the mathematical representation of the system. So we want to understand that without building a dam, how much of the area would take benefit from it, or how much hydropower electricity would we can generate. So what we will do, we would set up a simulation model without worrying about objective function. We will try to set up a hydrological model, for example. From hydrological model, we will try to set up a model for turbine, and we know that what kind of energy transformations are happening from potential energy to kinetic energy to electrical energy finally. So we'll try to write mathematical equations of this subsystems which we will put together, and we will say that we are trying to simulate a real world system to understand a behavior without spending millions of dollars by actually building the dam and then realizing it is not worth of it. And that is one power that water resource systems course will give us, that we should be able to identify the system, its boundaries, what are its constituents, and what kind of equations we should write for these systems so that we can model them mathematically. And as you can see that in water resources, we would look into reservoir operation for flood water management, for irrigation management, and our solutions would depend on various constraints such as how people are using the land, what is the regulatory or policy characteristics, and what are the rainfall that we got in a given year in that particular catchment. So we will talk about the uh, discharge curves for reservoirs as we go forward. Here is another example. Groundwater is a big policy as well as political issue in country like India, where we have already seen serious depletion of groundwater levels in states of Punjab and Haryana. And we say that that is going to be a menace as we move forward into 21st century. So we need better modeling techniques to understand how we can model this groundwater, what should be the optimal pumping rates, within the watershed where we should have these wells located, and the solutions that we are looking for would depend upon what are our objectives. We want to benefit farmers, we want to benefit industries, and we also want to make sure that although we are consuming a groundwater resource, ultimately it should translate into prosperity of for greater good. Then agricultural demands depending upon what kind of crops are being sown in what area. So Punjab, for example, is known for its rice or paddy fields, which are water intensive. So we have to account for the types of crops that can grow in that area. And finally, aquifer characteristics. Some areas they have groundwater available at reasonable height, so that may say that aquifer is little higher. On the other side, some areas already have depleted their groundwater to a level that is, we have to go down 100 to 120 feet. So aquifer characteristics also matter a lot, and there is a large regional or spatial variations in these aquifer characteristics. So we have to account for all these characteristics when we have to decide where we should have the bore wells located at the large scale. Again, you see that we are addressing these problems not at the field site. We are addressing this problem at much holistic or much regional scale, and that's where we should be able to formulate some of the equations based on the real world data sets. Now, just to give you an example of real world management system, since we are sitting in Gujarat right now, IIT Gandhinagar is situated in Gujarat, and we are not very far off from Narmada uh, river basin. And if you see that it starts all the way from Madhya Pradesh and touches the states of Maharashtra, Gujarat, with major portion of it flowing through Madhya Pradesh. So this is an interstate basin which cuts across many states, and all these three states depend upon Narmada Canal and this Narmada Basin to meet its water needs. And Gandhinagar is situated somewhere here around 230 kilometers north of Narmada, north of the Sardar Sarovar Dam, which is located somewhere here. And Narmada Canal takes off from Sardar Sarovar Dam, going through Gandhinagar, Ahmedabad, and then flowing towards the northwestern part of Gujarat all the way to Kutch. And you see that on this basin, you would see number of projects. So Bargi Dam, Tawa Dam, Indira Sagar Dam, Maheshwar Dam, Man Dam, and finally Sardar Sarovar Dam, in addition to Sukhi, Jobat Dam, Sukta Dam. And this is one specific basin where I was able to figure out around 10 to 12 water reservoir or water resource management projects just by eyeballing. And hence, wherever we have water as a scarce resource, these dams become even more important, as many people, in fact millions of people, depend on their greater good on these dams. So what we will try to do, we will try to represent these watersheds or basins as mathematical entities, try to understand or model the constraints, and without violating laws of physics, we will try to understand how we can design the systems to achieve flood control, manage the hydropower, and increase the efficiencies of turbines and hydropower projects that are situated at each of these reservoir locations, and also represent these things mathematically. So that was the same basin that I was showing, and now I have represented that basin with an arrow diagram to understand in which direction flow is happening. As soon as I do that, so this is the origin of Narmada river, and you see that many tributaries join this river at various locations, and these tributaries in turn also have these water resource projects, what we call as big reservoirs, into places, and hence it becomes a typical multi-reservoir problem, and the kind of objectives and constraints we would be dealing with would be hundreds in number, and that's where having a mathematical grounding is even more important. Also, whenever we talk about these large scale hydropower projects, one thing that always comes into picture is, are we maintaining enough socio-economic harmony, ecological harmony where we are building these dams? For example, whenever Narmada Dam was under construction, there was lot of movement, social movements took place, and I encourage you to look into them, where social activists were protesting against people being removed from the localities surrounding the dam, because whenever dams and reservoirs are built, it typically results in large scale flooding or inundation, and hence socio-economic harmony, forests around that site where reservoir is being built is always under radar of social activists, as well as can have huge potential to trigger uh, civil conflicts and civil disharmony. So that is also one important objective function that we have to keep in mind. That is, what is the cost is to benefit. If we are building a dam, is it at the cost of large number of livelihoods in short term, but in long term it is going to benefit the areas? And these questions are not easy to answer because a coin can sit on either side, and we will look into some of the quantitative aspect of it, or tangible versus intangible objective functions, as we go forward. And of course, in addition to these three functions, I have already mentioned that agricultural demands in different parts of the country or different parts of the region has to be taken care of as we are planning these multi reservoir projects. And final example that I would quote here is that how this interlinking of rivers uh, has what interlinking of river has to do with the water resource systems. So there have been many master plans and policy plans that have been prepared. That is, can we interlink the various rivers that flow in the country so that we can keep track of excesses and deficits. That means there are certain watersheds that may receive much more water. So I'm drawing one watershed here and another watershed here. So it may happen this particular watershed gets good share of rainfall, whereas this watershed receives scanty rainfall. And if we are able to connect these two watersheds through interlinking canals or rivers, we should be able to manage the deficits and excesses, and that would result in minimized flooding and minimized droughts into watersheds. And you can imagine that the costs involved, they are going to be huge. The ecological nuances associated would be huge. So that's why it takes a lot of time, both from policy as well as engineering side, for these plans to materialize. But the objectives are clear. We want to maximize the amount of transfer that can happen throughout this particular network, and the transfer has to be reliable. But that once we build this network by spending hundreds of millions of dollars, and then we realize that our entire assessment or mathematical modeling was incorrect, or we just did not did any mathematical modeling and all decisions were based on intuition, and after a couple of years this entire system is rendered useless because we overestimated or underestimated the amounts of transfers that can take place realistically in a real world watershed. So the concept of water resource system management has real world repercussions, and the costs can be in in the costs can be really large and could have detrimental effect if our solutions are not right. And then of course we want to also maximize the irrigation potential, that we are doing interlinkages of rivers so that all every pocket in the area where this interlinkage has happened can benefit from the water transfers. And we have to define certain measurable uh, objective functions. For example, is irrigation happening, or are we able to provide enough water to irrigation? Or if we are having some agricultural practices that are so native to that area, would that interlinking of river help us preserve those practices? So this is a sample map that I have taken for peninsular river system, which deals with it's a conceptual map of interlinkages of river, and you see Godavari, Krishna, Pennar, Kaveri, all the major rivers, and how the interlinking could look like. And you can imagine that it would not only require good understanding of hydrology, but also good understanding of policy, good understanding of culture, that what people prefer in each area, and finally the cost that we always want to minimize as we talk about objective function. And other areas include where may not go into that much detail, but I think it's worth mentioning if you want to take a look at it. Water quality management is one area where we can write or define objective functions. And in fact, I will give one assignment with certain pointers where you will form the first objective functions with constraints on the surface water quality management problem. Then we would also look into hydropower system management, that what is the reliable power a particular hydropower can generate. So there would be some dam, and this dam will have certain height. And we know that the fundamental principle of hydropower is that this potential energy of water is translated into kinetic energy by hitting it on turbine, and when the turbine rotates it is coupled with the generators and electricity is generated. This is a typical high school diagram of hydropower plant. But the questions here arises is that the storage here would depend upon how much height we have. This height in turn will determine that how much capacity we can that what would be the rotations this turbine can have, and this would be directly influencing how much electricity we can generate. So this would become an interlinked problem for which again we will write some mathematical equations and try to maximize the generation potential. Also, we want to estimate what is the reliable power. Is there 100% guaranteed power that this hydroelectric power plant is going to produce throughout the seasons? We understand during monsoons water would be there, but what would happen when monsoon is not there or rainfalls are not there? Can we have some reliable estimate of power so that we can build the associated redundancies and backups accordingly? And finally, the groundwater pumping decision is that how much we can rely on groundwater beyond engineering, beyond irrigation requirements. So the example that I discussed, that what are the objective constraints and sequential decisions that we have to make so that we are fully optimizing the use of groundwater pumping. And finally, I will conclude this lecture with the sustainable water resource management. Of course, we can define objectives that minimize the cost or maximize the instantaneous benefits. But whenever we talk about sustainable water resource goals, we are not only looking for now, but we are also looking in future while maintaining the social, ecological, environmental, and hydrological integrity. So these big words, we will try to quantify them, that how we can model, how we can measure, how we can mathematically express these functions, and then try to solve those equations to get the values on which actions can be taken. And some of the quantitative measures of resilience include that how vulnerable we are. What is the resilience of our systems now 10 years later, 30 years later, and towards the end of the design life? And finally, what is the reliability of meeting future demands? We have designed a system which is able to make everybody happy and prosperous today, but are we going to have same status after 30 years, 40 years, or we are going to soak up entire groundwater and hence end up with nothing after certain period of time? So this is how we can measure the sustainability of any water resource projects, and the productivity index, because agriculture would always be at the central piece whenever we talk about managing water resource systems. And industries also, specifically in states like Gujarat where we have industrial boom, and the water demand of industries is always going to be high. So can we measure the productivity per unit of water consumed? So these are some of the indices that we will inquire into as we go forward. With that, this is our first lecture where I've introduced you to the kind of problems or kind of questions that we will deal with, and uh, what constitutes water resource systems. Anything you see where humans are intervening into a water resources, we are basically saying that it's a managed system. And to make good optimum decisions around those water resources, systems would constitute the subject of water resource management. As we go forward, I will introduce this concept of systems more formally. We will discuss what are the various types of systems that we deal with in water before we go into the quantification aspects, where we will spend some considerable amount of time. Again, if you have any questions, please feel free to write me an email and I would be more than happy to answer. Thank you.